Alright, another video here, quick. Unit 2, multi-dimensional motion, worksheet 2. I'm going to write up these solutions real quick here. We'll see. Alright, we'd already talked about this a bit, so I'm just kind of picking up where we left off. Alright, so I had already done this part in the previous video. Displacement in each direction in terms of t. I started doing here, y direction from 0 to t. Delta x, we didn't finish this one. So let's go ahead and do this. Alright, this one is fairly straightforward. Let's see what we have here. So, delta x, 3.0 t cubed over 3 plus 4.0 t evaluated from 0 to t. Well, delta x equals t cubed plus 4t. Alright, good enough. Now, we talked a little bit about setting this up, right? We talked about this in the class, like what could this represent? It's an object falling and possibly getting blown forward or thrusting forward. It's firing an engine, right? It's moving forward at 4 meters per second. The engine turns on, it starts to accelerate, but it's not a constant acceleration. It's actually an increasing acceleration. So it's almost like it went off the cliff and it's falling, but it's blasting thrusters forward as it falls. So it's, it's maybe eventually going to take off back up. So the object starts in x coordinate of 0, 0 meters and moves for 5 seconds. Determine the object's final velocity and position in each dimension. Alright. So, so it starts at 0, right? So these equations here, delta x equals t cubed plus 4t. Well, remember, this is x final minus x initial equals t cubed plus 4t. Since the x initial we're saying is 0, I can just say, x final equals t cubed plus 4t. So the x final, which is actually x at 5 seconds, equals 5 cubed plus 4 times 5. So 5 to the third plus 20. Oops. Typing this in went awry. 5 third, hit the over arrow. 5 to the third plus 20 is 145. So the x at 5 seconds is 145 meters. Alright, delta y equals negative 5t, therefore y final equals negative 5 times 5 squared. So I guess it's negative 125, right? Harmon's going to just double check so that we don't make a fool. Y final equals negative 125 meters. Alright, now for the velocity, we can just plug in the velocity that's 5 seconds up here. So v5, vx, at 5 seconds should be 3 times 5 squared plus 4. Alright, so 3 times 25 plus 4, 79. 79 meters, and it's positive meters per second, Vy at 5 seconds is negative 10 times 5, or negative 50 meters per second. Alright, so we're going to try to put this all together, right? So after moving for 5 seconds, now has an x coordinate of 145, y coordinate of negative 125. It's moving at positive 79 meters per second in the x direction, and negative 50 meters per second in the y direction, right? Because this rate of change of acceleration is not very big. It's going to take a few seconds for it to even get up to gravity acceleration. So, sketch a diagram of its motion, including a path and its starting and ending point. Alright, so we can get that from here. Starting and end point positive 145, negative 125. So, you know, positive 145, negative 125. So you're right here, right? Now, how does it get there? What kind of shape does this take? Well, remember, it's already moving, and it's speeding up in the x direction, and it's falling in the y direction, right? So it's kind of like a, it's an arced path. It's going to arc like this, you know, because it starts off with no x velocity, right? So it's gonna fall like that. This path, this is where it gets to at 5 seconds. Determine the magnitude of the object's displacement. Alright, so we already figured out its final x and y position, right? Or essentially its displacement in the x and y direction. So the object's just, I don't know why I left space over here. It's weird. So now I just have to put in this. So, oh, that's why. I was going to draw a diagram. It's delta x is positive 145. Delta y is negative 125. The resultant displacement is the diagonal. Alright, this is r. Delta r vector. Alright, and we use Pythagorean's theorem. So 145 squared. I usually don't put in the negative sign. Sometimes people mess that up because you're squaring a negative number. You don't really need to put it in there. Man, that was all crooked there and that. Sorry about that. Just trying to do this kind of quick. 145 squared. Plus, see, I almost did it just then. I almost put in the negative sign. That would have been pretty funny, actually. So the magnitude of the resultant vector is 190 meters. To determine the final magnitude and direction of the object's velocity relative to the positive x-axis. So the final velocities here, we've got in the x direction, I think it was positive 90 meters per second. Is that right? Before I make a... No. Positive 79. Whoops. 79 meters per second. In the y direction, the velocity is negative 50 meters per second. So we're going to find the resultant of that. This is the final velocity. That's the velocity vector. This is the y, vx. Putting little arrows over it to represent the vector. We're going to also find that angle. Alright. So, v is going to be the square root of vx. And we typically don't put the vector symbols over these. These are magnitudes, so we don't need to put vector symbols over those variables. Alright, so v equals the square root of 79 squared plus 50 squared. Square root of 79 squared plus 50 squared equals about 93. Makes sense. It's got to be bigger than both of them, meters per second. Theta. Alright, so this side's 79, this side, so let me draw this triangle here. Alright. I'm not even put numbers on here. 79, 93, 50, and theta. I like to use the sides we were given, or the sides we already calculated, in case we made a calculation error here. So we'd say tan of theta equals opposite over adjacent, 50 over 79. So theta equals tan inverse, sometimes called the tanverse. No, we only call it that. No one calls it that. You should, but it's kind of interesting. Inverse tangent of 50 over 79. I am in degree mode. That's good. Theta is 32 degrees. 32 degrees below the positive x-axis, right? Where, you know, normal coordinate system, positive x-axis. So there you go on that one. All right, number 2. Quick do this one for you. Spacecraft moves in a horizontal plane powered by 2 perpendicular thrusters starting at a coordinate of 0, 0 and moves with the following velocity components. The thruster providing the x direction breaks off. The The thruster providing the x direction braking turns off once the x velocity reaches 0 meters per second. Where will the object be located when the x thruster shuts down? Holy moly. All right. Probably need more space for this one, Harmon. What are you doing? Let me get a little comfortable here. All right. So, when x velocity is 0, so we need to find the time. Find t when Vx equals 0, first of all. All right, so 0 equals negative 1t squared plus 900. So positive t squared equals 900. T equals square root of 900, which is 30, right? Man, I'm not confident in my mental math this year. Those months in quarantine slowed my brain down. It's embarrassing. All right, anyways, this is good. This get me back on track. So 30 seconds later, everything shut down. So where is it located? Well, we're going to have to take the integral of both these functions, people, and evaluate them over 30 seconds to figure out how far in each direction it moves. All right, so delta x equals the integral from 0 to 30 of negative t squared plus, at least they're nice numbers, 900 with respect to time. All right, so delta x equals negative t cubed over 3 plus 900, evaluate from 0 to 30. All right, so wait a minute. $30 cubed divided by 3 is what have I done? Something's weird here. Ah, Harmon, you fool. You probably saw it before I did. I forgot to put the t. I forgot to make it 900t. And I'm sitting here, wait a minute. This number is going to be bigger than this. All right, so here we go. Delta x, put in 30 for t. So it ends up being negative 30 cubed over 3 plus 900 times 30. All right. So it's negative 9,000 plus 900 times 30, which is delta x equals 18,000 meters or 18 kilometers. So it's moved pretty far forward. Now that thruster turns down, it's stopped. However, the whole time it was still moving in the y velocity. I don't know why we don't have a y velocity brake, but apparently we don't. So delta y equals from 0 to 30 of 5t dt. Delta y equals 5t squared over 2 from 0 to 30. So 5 times 30 squared divided by 2 is 2,250 meters in that 30 seconds. So I plugged in 30 for t there. So since we're saying the initial coordinate is 0, 0, x final equals positive 18,000 meters. Delta y is positive 2,250 meters. Where will the object be located 20 seconds after the thruster is shut down? Okay, so now we got to think about, okay, what's going to happen in each direction now? All right, so 20 more seconds of motion. So, well, in the x direction, right, we know that the velocity is 0 now. right? So this should read like for t less than or equal to 30 seconds, you know, because I can't just tell you that because I want you to figure that out. But after that, it doesn't keep running, right? Only the y velocity function keeps running. So after 20 seconds after the thruster shuts down, your x position is going to be still positive 18,000 meters, but it's going to keep moving in the y direction. All right, it's going to keep moving in the y direction. So basically, we're going to take this now and go another 20 seconds. But we can't go from 0 to 20, right? We got to go from 20 to 30, or sorry, from 30 to 50, and then add it to this, or we go from 0 to 50, because, you know, this would be 50 seconds total from start, right? All right, so x, at 30 seconds, the x doesn't increase anymore, but the y will, because there's still this force in the y direction propelling it. So, you don't need to reintegrate the whole thing. Delta y equals 5t squared over 2. And then it's just a matter of what you want to evaluate it over. So you could go from 30 to 50 and see how far it moves in that next 20 seconds. Or you could go back and calculate it all the way from 0 all the way to 50, because the y never changes. Believe it or not, I'm actually going to do it from 20 to 30 so you can see how that's done. So what you do is you plug in the time on top, 30 squared over 2, and you subtract off what you get if you substitute in the bottom. It's like x final minus x initial, basically. All right, so 5 times 30, and be careful in your calculator, because let me tell you something, it's easy to make a calculation error here. Minus 5 times, oops, I messed up the limits. This is 30 to 50. Alright, so this is 50, and this is 30. It's the next 20 seconds. That's my bad. You probably saw that again. It's getting late. I'm making mistakes. Alright, 50, 5 minus times 30 squared divided by 2. And I get 4,000. So, it moves 4,000 meters in those next 20 seconds. So, delta y total is 2250 plus 4,000, which is 6,250 meters. And if you just go and, if we had done it from 0 to 50, that would have been easier, because it would have just been the 6250. 5 times 50 squared divided by 2 gives me 6250. That would have been easier, but I don't know. It's worth seeing how you actually do that when you have two different numbers. Sketch the path of this object over this complete time interval. Oh man, I am annoying myself here. So, it starts here, let's say. It's going to go forward 18,000 meters in the x direction. Let's call that, I don't know, 18,000. Use dots, I guess. That's x final. Alright. And it let's see, it goes that way. Let's see, how does it do that? It slows down. So it has a big kind of positive velocity, and it's going to slow down, so that's going to get closer together. So I'm going to kind of keep track of the x direction here. Alright, these dots got to get closer together. He stops. Oh, somebody's crying. Hopefully it's not the sick daughter. We'll find out. I have to wrap this up. Now, in the y direction, okay, it's gonna keep accelerating, right? It starts at 0. After 30 seconds, it goes 2250, so it's gonna go, you know, like out to here. Then it's gonna go even farther over the next 20 seconds. So it's, if you imagine this being 50 seconds, it's going to go farther during the first, 3/5 than the last 2/5. So it's going to go during the, it's going to go farther during the last part. So it's going to get like out to here. And it's going to speed up. So the path is going to look kind of like this. Cool. Something like that. It's hard to figure that one out, right? Because it's gonna speeding up in the y direction, right? If I plot what's going on in the y direction, it's speeding up, getting farther apart. All right, that's about it. I'll scan that, get that posted. It took a while, but it was requested and I needed to get it done. All right, talk to you guys later.